A marble circles a heavy sphere on a stretched sheet, tracing a path that looks almost like a planet in orbit. But the real mystery is far deeper. Nothing in space is actually sinking downward. Mass changes the geometry of space and time itself, and every moon, planet, beam of light, and falling object follows the curves that geometry creates. In this journey, simple fabric becomes a doorway into Einstein's universe, where clocks slow near massive worlds, stars wobble around unseen companions, and gravity travels across the cosmos as waves. Thank you for spending part of your time here. If this kind of calm scientific exploration brings a little wonder to the day or a little peace to the night, please leave a like, subscribe for more, and share the video with someone who enjoys the quiet mysteries of the universe. What time is it where this is playing, and where in the world is it being watched? Leave a comment below. Now, let the surface stretch, the marbles begin to move, and the true shape of gravity slowly come into view. Gravity is among the most familiar features of existence, yet it remains one of the strangest. It shapes the fall of rain, the path of the moon, the structure of stars, and the gathering of galaxies across distances so vast that light itself needs ages to cross them. For centuries, gravity is described as a force reaching across empty space, pulling one body toward another. That picture works remarkably well for falling objects, planetary motion, and much of ordinary astronomy. It predicts where planets appear, how comets return, and how fast a stone accelerates near Earth. Yet the picture leaves a quiet question behind. How does one object act upon another across the emptiness between them? General relativity changes the question by changing the stage on which motion occurs. In this view, gravity is not primarily an invisible pull. It is the shape of space and time themselves. Matter and energy alter that shape, and objects move through the altered geometry along the most natural paths available to them. A planet circling a star is not being dragged around by a hidden rope. It is following a path through curved space-time, much as a traveller follows the bends of a road without needing a sideways force to explain every turn. The road itself determines which direction remains straight. This idea begins with a union that is difficult to picture because daily life separates space from time. Space seems to describe where something is, while time describes when it is there. Relativity joins them into a single structure called space-time. Every event has a place and a moment, and those two aspects cannot be fully separated. Motion through space affects the passage of time, and gravity affects it as well. Near a massive object, clocks run more slowly than clocks farther away. The difference is tiny near Earth, but it is real, measurable, and essential for technologies that depend on precise timing. Gravity therefore does more than guide motion. It also changes the rhythm by which moments pass. The familiar image of a stretched sheet offers a first glimpse of this idea. A heavy ball placed on flexible fabric creates a depression. A smaller ball rolled nearby curves inward because the surface beneath it is no longer flat. The smaller ball appears to be attracted to the larger one, yet its path is shaped by the surface it crosses. The demonstration makes curvature visible, turning an abstract geometry into a moving pattern. It also suggests that greater mass produces a deeper distortion. A heavier object bends the fabric more strongly, and nearby paths change more sharply. This echoes the central insight of general relativity. Mass and energy tell space-time how to curve, while curved space-time tells matter how to move. The relationship is mutual, continuous, and present everywhere. Earth curves space-time around it. The Sun curves it far more. A galaxy changes the geometry across an immense region, and a black hole bends it so severely that beyond a certain boundary, every possible future path points inward. Yet the sheet is only a guide, not the real thing. Its depression points downward into another dimension, while actual space-time does not need to sag into an external realm. Curvature can exist within a geometry without bending into something outside it. The surface of Earth offers a simpler example. It is curved, and lines that begin parallel near the equator can eventually meet near a pole, even though travellers on the surface never need to leave it. In the same way, space-time can possess its own internal curvature. The geometry is known through the behaviour of rulers, clocks, light, and freely moving bodies. The sheet model also uses ordinary gravity to explain gravity. The smaller ball rolls inward because Earth pulls it down along the sloping fabric. Real orbital motion requires no such downward direction beneath the universe. The model therefore succeeds as a visual metaphor while quietly hiding the deeper structure it tries to reveal. The real change is not a hollow in space alone. Time also bends, and in many ordinary situations the curvature of time plays the larger role in producing what appears as gravitational acceleration. An object released above Earth follows the straightest possible route through curved space-time. That route leads toward the ground. Even though the object feels no force while falling freely, a person standing on the surface feels weight because the ground prevents free fall. The surface pushes upward, forcing the body away from its natural path. This reverses common intuition. Falling feels like surrender to gravity, but in relativity, free fall is the closest available state to unforced motion. Standing still on Earth requires continual resistance from the ground. The sensation called weight is the pressure of that resistance. This principle becomes clear in orbit. Astronauts and spacecraft near Earth are not beyond gravity. Gravity there remains strong. They appear weightless because everything is falling together. The spacecraft, the equipment, and the people inside all follow neighbouring paths through curved space-time. None is supported by a floor in the ordinary sense, so no persistent pressure creates the feeling of weight. The orbit is a fall that continually misses Earth. Sideways motion carries the spacecraft forward, while curvature turns its path downward, and the planet's surface curves away beneath it. What looks like suspension is continuous motion along a natural route. The same principle governs the Moon, though on a far larger scale. The Moon falls around Earth. Earth falls around the Sun, and the Sun moves within the gravitational structure of the galaxy. No object occupies an absolute state of rest. Each follows a path shaped by nearby matter, distant matter, and its own motion through space-time. Even the central body responds. Earth does not circle a perfectly fixed sun. Both move around a shared centre of mass, though the Sun's much greater mass keeps that point deep inside it. The Moon likewise makes Earth wobble, as both bodies travel around their common balance point. The movement may be small, but it reveals that gravity is never truly one-sided. Every mass contributes to the geometry, and every mass responds to the combined geometry around it. The effect can often be ignored in simple calculations, but nature does not ignore it. General relativity replaces the old image of isolated pulls with a single connected structure. Matter, motion, distance, and time become parts of one system. A star changes the space-time around a planet. The planet makes a smaller change around the star, and both disturbances extend outward, weakening but never ending at a sharp border. When masses accelerate, changes in the gravitational field travel away as ripples in space-time. These gravitational waves move at the speed of light and carry information about violent events, such as merging black holes and colliding neutron stars. Their detection confirms that the geometry is not a fixed background. It can stretch, compress, and transmit change. Space-time is not merely an empty container in which the universe happens. It participates in the happening. This is the first great shift in visualizing gravity. The ordinary picture begins with objects and adds a force between them. Relativity begins with a geometry shaped by all forms of mass and energy. Motion then unfolds within that geometry. The difference can appear subtle when a ball falls from a hand, yet it becomes profound near dense stars, in precise clocks, in the bending of light, and across the expanding universe. Gravity becomes less like a thread pulling bodies together and more like a landscape that determines which paths are possible. The landscape cannot be seen directly, but its contours appear in every orbit, every falling object, every delayed clock, and every beam of light that curves near a massive body. This geometry also changes what straightness means. In flat space, a straight line keeps a constant direction, and parallel lines remain apart. In curved space-time, the straightest paths can converge, separate, or circle a massive body. Light follows these paths as faithfully as matter does, even though light has no rest mass. A distant star can therefore appear displaced when its light passes near the sun, and a galaxy can act as a gravitational lens, magnifying or multiplying the image of something farther away. These effects are not decorative details around the theory. They reveal that curvature belongs to the root itself. The beam is not pulled sideways through an otherwise rigid emptiness. The emptiness has acquired structure, and the beam traces that structure with remarkable precision. The deeper mystery is not simply that mass bends space and time. It is that space and time are capable of bending at all, and that this hidden geometry governs the motion of everything from dust to galaxies, while remaining almost invisible to ordinary sight. A flexible sheet becomes useful because gravity itself is invisible. No eye sees space-time curve around a planet, and no hand feels the geometry directly. What becomes visible instead is motion. A moon circles, a stone falls, a beam of light bends, and a clock runs at a slightly different rate. The stretched surface gathers several of these effects into one quiet image. A heavy sphere rests near the centre, the fabric dips around it, and smaller spheres change direction as they cross the sloping surface. The demonstration is simple enough to understand at a glance, yet rich enough to suggest a deeper idea. The heavy sphere does not reach outward with a visible hook. It changes the conditions around itself. The surrounding region is no longer flat, so motion through that region is no longer the same. This is the first strength of the model. It shifts attention away from a mysterious pull and toward a changed landscape. The surface represents space-time. The large sphere represents a massive body, and the smaller spheres represent objects moving through the geometry created around it. Greater mass produces a deeper depression, while a tighter sheet resists deformation more strongly. The visual connection is immediate. More mass means more curvature, and more curvature means a greater change in nearby paths. A marble rolled far from the central weight may travel almost straight. A marble passing close by may turn sharply. A marble launched with the right speed may circle several times before losing energy to friction and spiraling inward. Each path makes the hidden geometry visible through motion. The demonstration also reveals that curvature is not confined to a single point. The deepest part lies beneath the mass, but the slope extends outward. The effect weakens with distance rather than ending at a clear edge. This resembles real gravity, which also fades gradually. Earth influences the moon. The sun influences distant planets. And the combined mass of a galaxy shapes stars far from its centre. No hard boundary marks the end of a gravitational field. The geometry becomes gentler with distance, but it remains part of the larger structure. On the sheet, the central depression gives this idea a form that can be seen. A nearby marble reacts strongly, while one near the edge may only drift slightly from its original course. The model becomes even more revealing when two heavy spheres are placed on the fabric. Each creates its own depression, but the surface cannot keep the two distortions separate. Their slopes overlap and combine. Smaller objects then respond to the total shape rather than to either mass alone. This resembles the way real gravitational fields add together. The Earth-Moon system, for example, creates a joined geometry through which spacecraft must travel. Near Earth, Earth's influence dominates. Near the Moon's influence becomes more important. Between them, the shape is more complicated than a single smooth hollow. The model allows this complexity to appear without requiring equations. It turns a field produced by several masses into a surface that can be watched as it shifts. Yet the sheet also introduces a subtle misunderstanding. The large sphere appears to remain fixed while the smaller one rolls around it. But in reality, both bodies respond. A planet pulls on its star as surely as the star pulls on the planet. The star usually moves less because it has much greater mass, but it still moves. Both bodies orbit a shared center of mass. On the sheet, a heavy central sphere may barely shift because friction and the support structure hold it in place. The result can make gravity appear one-sided. A better demonstration allows both spheres to move freely. Then the larger mass drifts slightly as the smaller one circles, and the system begins to show the mutual nature of gravity. This small motion matters. Astronomers detect unseen planets by measuring the tiny wobble they produce in their stars. The visible star does not sit perfectly still. It moves around the system's shared balance point, carrying the signature of an orbiting world. The flexible surface can hint at this relationship, though it cannot reproduce it perfectly. The material itself has weight, tension, and friction. Real space-time is not cloth. It does not stretch because it hangs in Earth's gravity, and orbiting bodies do not rub against it as marbles rub against fabric. A marble on the sheet loses mechanical energy as sound, heat, and internal motion. Its orbit shrinks, and it eventually falls into the center. A planet in nearly empty space does not experience this kind of drag. Its orbit can remain stable for immense spans of time. This difference is among the most important limits of the analogy. The spiral inward looks dramatic, but it is usually a property of the model rather than of ordinary planetary gravity. Real systems can lose orbital energy, but they do so through other processes. Atmospheric drag lowers the orbit of satellites close to Earth. Tidal interactions transfer energy between rotation and orbital motion. Accelerating masses can also radiate gravitational waves, though this effect is extremely weak for planets and becomes important mainly in compact systems such as closely orbiting neutron stars or black holes. The sheet compresses these very different processes into one simple spiral, so its apparent realism must be treated carefully. Another limitation lies in the missing dimension. The fabric is a two-dimensional surface that curves downward into the three-dimensional space around it. Real gravity acts in 3 dimensions of space and 1 dimension of time. Earth does not create a funnel pointing in some universal downward direction. Its curvature surrounds it in every direction. Objects can orbit above any point on the planet, and the geometry has no preferred underside. The downward dip of the sheet is only a visual device. It translates an invisible mathematical curvature into a shape that ordinary vision can grasp. The danger appears when the translation is mistaken for the thing itself. Space-time does not need an external room into which it bends. Its curvature is measured internally, through the behavior of paths, distances, and clocks. A creature confined to the surface of a sphere could discover that the surface is curved without ever seeing the sphere from outside. It could draw large triangles and find that their angles add to more than the amount expected on a flat plane. It could send travelers along initially parallel routes and watch those routes approach one another. In a similar way, physicists infer the curvature of space-time from what matter and light do within it. The geometry reveals itself through relationships, not through a visible sag. Time is the largest absence in the sheet model. The fabric represents space-time. But what appears on the table is almost entirely spatial. General relativity, however, links gravity deeply to the rate at which time passes. Near a massive body, time runs more slowly relative to a region farther away. A clock at sea level and a clock on a mountain do not accumulate time at exactly the same rate. The difference is extremely small, yet precise instruments can measure it. Satellite navigation systems must account for gravitational and motion-related changes in clock rates. Without these corrections, position errors would grow rapidly. No marble on cloth can fully show this. The sheet suggests that distance and direction change near mass, but it cannot display the altered flow of time that belongs to the same geometry. This missing feature explains why the analogy remains introductory rather than complete. It gives shape to one part of the idea while leaving the deepest part unseen. Even so, the model has unusual educational power because it allows many gravitational behaviors to appear in one place. A gentle roll produces a deflection. A faster roll produces a wider orbit. A slower roll produces a tighter path. Two masses create an overlapping landscape. Several marbles reveal interactions, scattering, collisions, and the gradual emergence of preferred motion. The surface becomes a small laboratory of patterns. Its value does not depend on perfect accuracy. Its value lies in changing intuition. Gravity begins to look less like an invisible hand and more like the consequence of a world whose geometry is active. The central mass alters the stage, and motion follows the stage's shape. Once that shift occurs, the sheet can be left behind. The fabric is not space-time, the depression is not a literal cosmic funnel, and the spiraling marble is not a faithful planet. Yet the demonstration opens a door. It makes room for the idea that emptiness is not truly empty, that geometry can carry physical meaning, and that a body may change direction without being pulled in the ordinary mechanical sense. The visible curve on the table becomes a temporary guide toward an invisible curvature that reaches through every orbit, every falling path, and every region where matter changes the passage of time. A freely moving object near a massive body appears to turn, accelerate, or fall, yet general relativity describes its motion in a surprisingly different way. The object is not being pushed off a straight path by a conventional force. It is following the straightest path available through curved space-time. This path is called a geodesic. On a flat sheet, a geodesic is simply a straight line. On a curved surface, the geodesic may look bent when viewed from outside, even though it remains locally straight at every point. A ship crossing a spherical ocean follows the shortest route along a great circle. On a flat map, that route may appear curved, but on the globe it is the natural path. Gravity works through a deeper version of the same principle. A planet, a moon, a falling stone, and a beam of light all trace geodesics through a geometry shaped by mass and energy. Their motion can look like attraction, but the geometry itself guides the route. The distinction is subtle because ordinary experience is dominated by surfaces that resist free fall. A stone resting on the ground does not follow its natural geodesic. The ground pushes upward and prevents the stone from falling toward Earth's center. When the stone is released, that support disappears. It begins to move along the path that curved space-time permits. In this sense, the fall is not the forced state. Rest on the ground is the forced state. The stone accelerates toward Earth because the local definition of straightness changes from place to place. Nearby geodesics that begin side by side may slowly converge. The stone and Earth both respond to this geometry, though Earth's much greater mass makes its motion almost impossible to notice in the simple event. The same principle explains why a person in a falling lift would briefly feel weightless. Everything inside falls together along neighbouring geodesics. The floor no longer presses upward with its usual support, so the sensation of weight disappears even though Earth's gravity remains present. This observation forms the heart of the equivalence principle, one of the foundations of general relativity. Within a small, freely falling region, gravity can seem to vanish. Objects float because all are sharing the same natural motion, yet the disappearance is only local and temporary. Across a larger region, small differences in the gravitational field remain. These differences are called tidal effects. They reveal that spacetime is truly curved rather than merely described from an accelerating viewpoint. Two falling objects separated vertically do not follow perfectly parallel paths. The lower one is slightly closer to Earth and experiences a different geometry. Two objects separated sideways may drift toward one another because their paths aim toward the planet's centre. In a sufficiently small room, these differences are nearly invisible. Across a larger distance, they become measurable. Curvature announces itself through the changing separation of neighbouring geodesics. This gives gravity an unusual character. At a single point, free fall can remove the sensation of gravity. Across an extended region, gravity returns as relative motion between nearby paths. No choice of motion can erase the curvature everywhere. The sheet model hints at this when two marbles rolled beside one another gradually approach as the fabric slopes inward. Each marble follows the local surface, and their paths converge because the surface itself changes. Yet the real effect is not caused by rubbing against cloth or by a downward pull beneath a table. It comes from the internal geometry of spacetime. The geometry determines which trajectories count as unforced, and those trajectories need not remain parallel. An orbit is one of the most striking examples. A planet moves forward through space, but the spacetime around the star is curved. The planet therefore follows a geodesic that repeatedly bends around the star. Locally, it is always falling freely. Globally, its path closes into an ellipse or nearly closes while slowly shifting under relativistic effects. No engine keeps it aloft. No invisible structure holds it at a fixed distance. Its motion and the curvature fit together so that the planet continually falls around the star rather than directly into it. The same description applies to a satellite around Earth. With too little sideways speed, the path intersects the ground. With enough sideways speed, the surface curves away as quickly as the satellite falls. The result is orbit. Greater speed can produce a wider path, while still greater speed can lead to escape. These outcomes arise from the relationship between motion and geometry, not from separate kinds of gravitational pull. The idea becomes more difficult when time enters the picture. A moving object does not travel through space alone. It traces a path through space-time, often called a world line. Even an object that appears motionless in space continues forward through time. Near a massive body, the structure of time differs from that farther away. Clocks deeper in a gravitational field run more slowly when compared with clocks higher above. This change in temporal geometry contributes strongly to the motion seen as falling. The object follows the straightest route through a spacetime in which time itself is unevenly shaped. A purely spatial picture can therefore mislead. The planet is not simply rolling through a curved three-dimensional bowl. It is moving through a four-dimensional structure where spatial directions and rates of time are connected. The geodesic is the natural path through that whole structure. Light follows geodesics as well. Since light has no rest mass, An older force-based intuition might suggest that gravity should not affect it. Yet light passing near the Sun changes direction, and light from a distant galaxy can curve around a massive cluster. General relativity explains this without assigning weight to the light. The path bends because the geometry through which the light travels is curved. A massive object changes the possible routes between source and observer. Several routes may become available, producing multiple images of the same distant object. The image can stretch into an arc or brighten as the intervening mass acts as a gravitational lens. In extreme alignments, light may form a ring around the lensing body. These effects make curvature visible across cosmic distances. They also show that geodesic motion is universal. Matter and light respond to the same underlying geometry, though they travel through it in different ways. Massive objects move along time-like geodesics, while light moves along null geodesics, paths for which the ordinary separation between space and time reaches a special limit. The terms are technical, but the central idea remains simple. The geometry defines natural motion for everything. This universality is one reason general relativity is so powerful. It does not require a separate gravitational rule for every kind of object. A stone, a planet, a pulse of light, and a cloud of gas all respond to the same curved space-time. Their differences come from their initial motion, their physical structure, and the other forces acting upon them. Gravity enters as the common geometry beneath those differences. When no other force interferes, each follows its geodesic. When pressure, friction, magnetism, or a solid surface changes the motion, the object departs from that natural path. The sensation of force appears precisely when something prevents geodesic motion. A rocket engine pushes a spacecraft away from free fall. The ground pushes a standing body upward. A chair presses against a seated person. These everyday forces are real. But gravity in general relativity belongs to a different category. It is not something added to motion. It is part of the definition of unforced motion itself. The distinction becomes most dramatic near a black hole. Far from it, geodesics may curve gently and allow stable orbits. Closer in, the range of possible paths narrows. Beyond the event horizon, every future-directed geodesic leads deeper inward. The object does not encounter a solid barrier at the horizon. Locally, it may cross without feeling an abrupt impact. The decisive change lies in the geometry of possible futures. Continuing inward becomes as unavoidable as continuing forward in time. This extreme case reveals the full meaning of curved space-time. Geometry does not merely bend a route that could otherwise remain straight. It determines which directions can exist as future motion. Yet the same principle is already present in the fall of a stone and the orbit of the moon. At every scale, objects follow the natural paths allowed by the geometry around them. Gravity appears as attraction only when those paths are viewed from outside their local frame. From within free fall, the motion is quiet, unforced, and almost ordinary. The deeper strangeness lies in the fact that straightness itself is no longer fixed. It changes with mass, energy, and position, turning the architecture of space and time into the hidden guide behind every fall and every orbit. Gravity never belongs to only one body. A star curves the space-time around a planet, but the planet also curves the space-time around the star. The difference lies in scale, not in kind. The star usually dominates because it contains far more mass, so the planet's effect appears small, almost hidden beneath the larger distortion. Yet the effect remains real. Neither body moves around a perfectly fixed point. Both respond to the total geometry they create together, and both travel around a shared center of mass. This mutual motion is easy to overlook because everyday examples often place one object at the center and treat it as immovable. A stone falls toward Earth. The Moon circles Earth, and the planets travel around the Sun, while the larger bodies seem unchanged. These descriptions are useful approximations, but Earth responds to the stone and Moon, and the Sun shifts in response to every planet. Gravity is always a relationship, and every participant helps shape the motion. The shared center around which two bodies move is called the barycenter. Its position depends on their masses and the distance between them. When one body is much more massive than the other, the barycenter lies inside the larger body, often near its center. When the masses are more similar, the barycenter can lie in open space between them. Earth and the Moon provide a clear example. Earth is far more massive, so the balance point remains inside Earth, but it does not sit at Earth's exact center. As the Moon moves around, Earth also makes a smaller orbit around this internal point. The result is a gentle wobble. The familiar language of one body orbiting another remains convenient. Yet the deeper picture contains two simultaneous orbits, one broad and one narrow. The same is true of the Sun and Earth. Their shared center lies deep inside the Sun because the Sun is vastly more massive. Earth travels through its large yearly orbit, while the Sun follows a tiny corresponding loop. Jupiter produces a stronger effect, because Jupiter contains more mass than all the other planets combined. The balance point between Jupiter and the Sun can lie near or even beyond the Sun's visible surface, depending on their separation. The Sun therefore does not sit motionless at the center of the solar system. It continually shifts under the combined influence of the planets, tracing a complicated path around the solar system's overall barycenter. Each planet contributes, so the central star moves within the system it appears to command. This motion has become one of astronomy's most useful clues. A distant planet may be too faint and too close to its star to be seen directly, but its gravitational influence can reveal its presence. As the planet and star orbit their shared center, the star moves slightly toward and away from Earth. That motion changes the wavelength of the star's light. When the star approaches, the light shifts toward shorter wavelengths. When it recedes, the light shifts toward longer wavelengths. By measuring this repeating pattern, astronomers can infer that an unseen companion is present. The amplitude and timing of the wobble reveal information about the companion's orbit and minimum mass. The method depends on a simple truth: the planet does not merely travel around the star also responds. A second method watches the star's position against distant background stars. With sufficient precision, this astrometric wobble traces motion around the barycenter. In both methods, the hidden planet becomes visible through the motion it gives to the star. The flexible fabric model can hint at this mutuality when two heavy spheres rest on the surface. Each makes a depression, and the shape between them changes. If neither sphere is fixed, both can move. The smaller one may circle widely, while the larger one shifts more gently. Yet the demonstration often fails to show the balance accurately. Friction grips the spheres. The fabric resists motion, and the frame may hold the larger mass nearly in place. Real spacetime has no cloth fibers dragging against planets, and no table supports a central star. The model therefore needs interpretation. The visible depression is useful, but the most important lesson comes from allowing the supposed center to move. Once that happens, gravity appears less like obedience to a dominant object and more like a shared response to a common geometry. General relativity deepens this picture. In the simplest language, each body changes the space-time around it, and both follow geodesics through the combined curvature. The geometry is not divided into separate layers. It forms one dynamic field determined by all matter and energy present. The star affects the planet's path. The planet affects the star's path. and their motion alters the gravitational field through which future motion occurs, in weak fields and slow motion. The result closely matches the older Newtonian description of mutual attraction. Near compact objects or at extreme precision, the relativistic structure becomes essential. Two neutron stars orbiting one another provide a more intense example. Their masses may be comparable, so neither acts as a fixed center. Both race around a barycenter between them, strongly curving the surrounding space-time. As they accelerate, they emit gravitational waves. These waves carry energy away, causing the orbit to shrink gradually. The stars move faster until they collide, releasing radiation and creating heavy elements in the expanding debris. Here, mutual motion is impossible to ignore. The two bodies shape a violently changing geometry, and the changing geometry carries a record of their final approach across the universe. Binary black holes reveal the same principle in an even more extreme form. Two black holes orbit a point where no material object sits. As the orbit tightens, gravitational waves carry energy away until the holes merge. The final black hole settles, sending fading vibrations through space-time. Detectors register a pattern that encodes the masses, spins, and orbital history of the pair. The signal exists because gravity is mutual and dynamic. A fixed central object with a passive companion could not produce the same changing geometry. Even in calmer systems, shared motion shapes structure. Double stars circle common centers for millions or billions of years. A star can pull material from a companion when one expands and fills the region where its gravity can hold matter securely. Galaxies orbit within groups, though their motion is complicated by dark matter, gas, and many interacting members. Clusters of galaxies move through a collective gravitational landscape created by visible matter and unseen mass. At every scale, the idea of a single unmoving source becomes less accurate. The universe contains relationships of motion nested within larger relationships. The Moon and Earth move around their barycenter. That pair moves around the Sun. The Sun moves in response to the planets while traveling around the center of the Milky Way. The galaxy moves within the local group, and the group moves within still larger cosmic flows. No center remains absolute. Mass, distance, and arrangement determine which contributions dominate. A nearby star shapes a planet's orbit far more strongly than a distant galaxy, while the planet's influence on the galaxy is almost nothing. Approximation remains necessary because calculating every contribution at once would be impossible in practice. Astronomers choose a useful frame, treat dominant masses carefully, and ignore influences too small to matter for the question at hand. Yet the ignored effects do not vanish from nature. They remain beneath the approximation, waiting to become visible when measurements improve or when greater precision is required. The wobble of Earth caused by the Moon is often irrelevant to a simple satellite orbit, but it matters in precise navigation and in understanding the Earth-Moon system. The Sun's response to Jupiter may be negligible in a basic classroom diagram, but it becomes central when searching for planets around other stars. The lesson is that stillness is often an illusion created by scale. A massive body can appear fixed only because its motion is small compared with the motion around it. Once observation becomes precise enough, the center begins to move. Gravity then reveals its more complete character. It is not a command issued by one mass to another. It is a shared geometry in which every mass participates. Every orbit contains a counter-orbit, and every apparently stable center carries some trace of the bodies around it. The universe does not arrange motion around perfectly immovable anchors. It builds systems around shifting balances, and those balances quietly record the presence of worlds, stars, and dark companions that may otherwise remain unseen. An orbit begins with a fall that never reaches the ground. A stone released from rest above Earth drops almost directly downward because it has little sideways motion. A stone thrown horizontally also falls, but while it descends, it moves across the surface. Throw it faster, and it travels farther before reaching the ground. In principle, if it moves sideways quickly enough and no atmosphere slows it, Earth curves away beneath it at the same rate that it falls. The stone then remains in free fall, always descending toward Earth and always missing it. That continuing miss is an orbit. The stretched sheet model makes this pattern visible. A marble released near a central weight rolls inward along the slope. A marble given a sideways push follows a curved path instead. Its forward motion carries it across the fabric while the slope continually turns that motion toward the center. With too little speed, the marble reaches the central mass quickly, with more speed. It loops around before arriving. With a carefully chosen speed, it may circle several times. In the relativistic picture, the marble suggests an object following the most natural route available through a curved geometry. Sideways motion prevents a direct fall, while curvature prevents a straight escape. Together they produce a path that closes around the central body. In real space, a stable circular orbit is a special case. The orbiting body must have the right sideways speed for its distance from the central mass. If it moves too slowly, its path dips inward. If it moves too quickly, its path rises outward. A slightly slow or fast body does not necessarily crash or escape. It often enters an ellipse, approaching the central body at one part of the orbit and moving farther away at another. Nature commonly produces ellipses because exact circular conditions are rare. Planets, moons, comets, asteroids, and artificial satellites all follow paths shaped by their speed, direction, and position when the orbit begins. Gravity continually changes the direction of their motion, but in an ideal two-body system it does not steadily remove their energy. This is where the fabric model becomes misleading. A marble rubbing against cloth loses energy as heat, vibration, and sound. Each circuit becomes smaller, and the marble spirals toward the center. A planet moving through nearly empty space does not rub against space-time. It can remain in orbit for an immense span because its motion is not being drained by the geometry itself. The curvature guides the path without acting like a resisting material. Real orbital decay requires some process that carries energy away. A low satellite can encounter the thin upper atmosphere and slowly descend. Tidal interactions can transfer energy between rotation and orbit. A compact pair of neutron stars or black holes can lose energy through gravitational waves. Yet for an ordinary planet circling a star, these effects are usually tiny over human timescales. The persistent spiral seen on fabric is therefore not a normal feature of gravity. It belongs mainly to friction in the demonstration. Even with that limitation, the model reveals how sideways speed changes the character of a fall. The same depression can produce several outcomes. A gentle push leads inward quickly. A stronger push creates a tight ellipse. A carefully directed push produces a wider orbit. A very strong push may carry the marble across the sheet and away from the center. In real gravity, this final case corresponds to escape. Every massive body has an escape speed, the minimum speed needed to move away without eventually returning, assuming no additional thrust and no other major influence. Escape means the object has enough energy that its path remains open rather than closing into an orbit. It slows as it climbs outward, but it never turns back. The difference between orbit and escape is written into the geometry of the path and the energy of the motion. Sideways motion also explains why orbiting bodies do not require constant propulsion. A satellite does not need an engine to keep moving around Earth once it reaches a suitable orbit. Engines are used to launch it, adjust its path, or counter disturbances, but the orbit itself is free fall. The satellite moves naturally through the curved spacetime around Earth. This is why astronauts inside an orbiting spacecraft appear weightless. The craft is not hovering above the planet, it is falling along with everything inside it. The floor does not continuously hold the astronauts away from their natural path, so the usual sensation of weight disappears. A loose object remains beside them because it shares nearly the same geodesic. The quietness of orbit hides the speed and the fall beneath it. Orbital motion becomes more complex when more than two bodies are involved. The Moon travels around Earth, but the Sun also shapes its path. Earth and the Moon move together around the Sun, while the Moon follows a smaller motion around their shared barycenter. A spacecraft travelling between Earth and the Moon responds to both bodies and also to the Sun. Its route can curve in ways that look strange when drawn on a fixed page. A path may loop around one body, pass near another, and return without resembling a simple circle. In a changing gravitational landscape, an efficient trajectory often uses the motion of the bodies themselves. Spacecraft can gain or lose speed through gravitational assists, passing near a planet and exchanging a tiny amount of momentum with it. The planet's motion changes by an immeasurably small amount, while the spacecraft's path can change dramatically. The direction of the initial push matters as much as its speed. A purely sideways launch can produce an orbit. A launch aimed partly inward creates a different ellipse. A launch aimed partly outward may first climb before returning. This is why orbital navigation requires precision. Small differences in speed or direction can grow into large differences in position after many hours or days. Yet the underlying motion remains simple in principle. Once released, the object follows the route determined by the geometry and its initial conditions. Engines alter the route by changing those conditions. Gravity then carries the object along the new path. General relativity adds corrections that become visible when gravity is strong or measurements are precise. An elliptical orbit does not always return to exactly the same orientation. The closest point can slowly advance, causing the ellipse to rotate over time. Other planets create much of this effect in the solar system, but spacetime curvature adds a smaller contribution. Mercury reveals this clearly because it moves close to the Sun, where the curvature is stronger. Its orbit carries a subtle shift that the older gravitational picture does not fully explain. General relativity accounts for the remaining motion by treating Mercury as following a geodesic through the Sun's curved spacetime. The orbit is nearly an ellipse, but the geometry prevents it from closing perfectly. This small deviation becomes evidence that gravity is not merely a force acting across a fixed stage. The stage itself shapes the path. Near a black hole, the relationship between sideways motion and curvature becomes even more extreme. Far away, stable orbits can exist much as they do around stars. Closer in, stable circular paths become impossible. An object with sideways motion may circle briefly, but a small disturbance can send it inward or outward. Light itself can follow a circular route at a special region, though that orbit is unstable. A tiny change sends the light away or into the black hole. These paths show that orbit is not a universal balance that works at every distance. It depends on the structure of spacetime around the central mass. As curvature grows stronger, the range of stable motion narrows. The stretched sheet hints at this through its steep central slope. But the true geometry is more subtle because time bends along with space. The deeper lesson is that orbit does not oppose falling. Orbit is falling transformed by sideways motion. A moon remains aloft not because it escapes gravity, but because it belongs completely to gravity's geometry. It follows a natural path that circles through curved space-time, carrying forward momentum into an endless descent that never arrives. The same principle holds from small satellites to planetary systems, and from binary stars to matter moving near black holes. A sideways push changes a plunge into a loop, and that loop reveals one of the quietest forms of motion in the universe, continuous fall shaped into lasting order. A circular orbit appears calm because its distance from the central body remains almost unchanged. The object moves sideways while gravity continually turns its path inward, and the balance repeats from moment to moment, yet the circle is only one possibility within a wider family of motion. Most natural orbits are ellipses, stretched circles with one body located away from the geometric center. Along such a path, the orbiting object does not move at a constant speed. It travels faster when it approaches the central mass and slower when it moves away. The changing speed reflects an exchange between motion and position within the gravitational field. Near the central body, the object has less gravitational potential energy and more kinetic energy. Farther away, it has more potential energy and less kinetic energy. In an ideal orbit, the total remains constant. Nothing is being lost. The object simply moves through different parts of the same gravitational landscape. A stretched sheet can show some of this behavior. A marble launched around a central weight may follow a visibly elongated path. It sweeps close to the center, turns sharply, then climbs outward and slows before curving back. The shape resembles an ellipse, and the speed changes in the expected way. The closer pass is faster, while the outer arc is slower. A gentle sideways motion creates a narrow ellipse. A stronger one creates a broader orbit. A carefully balanced push approaches a circle. These patterns reveal how one gravitational environment supports many trajectories depending on starting position and velocity. Yet the demonstration also creates a persistent misunderstanding. The marble doesn't remain on a clean ellipse. Its path slowly contracts. Each loop carries it closer to the central mass until it finally collides or settles at the bottom. The shrinking motion looks like a realistic consequence of gravity, but under ordinary conditions it is not. The marble spirals inward because the fabric and surrounding air remove energy. Rolling friction deforms the surface and the marble. Tiny vibrations spread through the frame. Sound carries energy into the room. Air resistance adds another small loss. The orbit decays because the demonstration continually transfers energy to its environment. A planet moving through nearly empty space behaves differently. Space-time does not act like cloth rubbing against a sphere. The planet can follow an ellipse for an immense span without steadily losing orbital energy. Its path may change because of other planets, tides, radiation, stellar mass loss, or relativistic effects. But there is no ordinary drag caused by moving through curved space-time. This difference marks the boundary between the picture and the physics. The sheet is good at showing curvature and deflection, but poor at preserving energy. Real celestial systems can spiral inward, though the cause must be identified carefully. A satellite in low orbit around Earth passes through the thin upper atmosphere. The air is sparse, but the satellite moves so quickly that even a small resistance matters over time. Drag removes orbital energy. The satellite drops into a lower orbit, where the atmosphere is denser, so the decay accelerates. Eventually it re-enters. This resembles the shrinking path on the sheet. But the cause is atmospheric resistance, not gravity alone. A moon can also change its orbit through tides. The gravitational pull across an extended body is not perfectly uniform. The near side experiences a slightly different pull from the far side, creating tidal bulges and internal friction. This allows rotational energy and orbital energy to move between bodies. Earth rotates faster than the Moon travels around it, so the tidal bulge carried ahead by Earth's rotation gives the Moon a small forward pull. The Moon gains orbital energy and slowly moves farther away, while Earth's rotation gradually slows. Other systems behave differently. A moon orbiting faster than its planet rotates can lose energy and move inward. Tidal effects can therefore produce outward migration or inward spiraling. The direction depends on the relationship between rotation and orbital motion. Gravitational waves provide another path to orbital decay. Two dense objects moving around one another disturb spacetime in a changing pattern. The disturbance travels outward as waves, carrying energy and angular momentum away. As the orbit loses energy, the bodies draw closer and move faster. The process is negligible for ordinary planets because their masses and speeds are too small to produce a measurable loss over short times. For neutron stars and black holes, it becomes decisive. The orbit tightens, the wave frequency rises, and the pair enters a final accelerating spiral before merger. Here, inward motion is not caused by friction with a material medium. Energy leaves through the geometry itself as radiation. The contrast is important. The sheet marble spirals because energy leaks into cloth, air, sound, and heat. A compact binary spirals because gravitational waves carry energy across the universe. The visible shape may look similar, but the mechanism is entirely different. Circles and ellipses also reveal the role of angular momentum. Angular momentum describes rotational motion in a system. It depends on mass, speed, and distance from the center. In an isolated orbit, angular momentum remains constant. As an object moves inward along an ellipse, it speeds up. As it moves outward, it slows down. The same principle appears in a spinning skater who turns faster when drawing the arms inward. Though the orbital case involves motion around an external center, conservation of angular momentum helps explain why a falling object with even a small sideways motion usually does not plunge directly into the central mass. As the distance decreases, the sideways speed increases, the path swings around, producing an orbit or a close pass unless energy is removed or the trajectory intersects the surface. A direct collision requires unusually precise alignment. This is why disks form so often in astronomy. Gas falling toward a young star, a compact object, or the center of a galaxy carries some angular momentum. Different streams collide and lose disordered motion, but shared rotation remains. The material settles into a flattened disk rather than falling straight inward. Friction within the disk can move angular momentum outward while allowing some matter to spiral inward. Here again, a spiral appears only because energy and angular momentum are transferred. The spiral is not the default shape of free motion. It is the signature of interaction. Elliptical orbits can also change without losing energy. Additional bodies disturb them, shifting their orientation and shape. A planet may pull gently on another planet during each pass, producing small changes that accumulate. The closest point of an orbit can rotate. The tilt can vary. The ellipse can become more or less stretched. In a system with many bodies, no orbit remains perfectly fixed. The solar system is stable over long periods, yet it is not frozen. Its planets continually exchange tiny gravitational influences. These perturbations do not usually create simple inward spirals. They produce a slow evolution of orbital elements. The sheet demonstration often turns every disturbance into rapid decay because friction overwhelms the subtler effects. Real space is far less inclined toward quick visual drama. Its changes are often distributed across centuries, millions of years, or longer. Even a circle is less permanent than it seems. A circular orbit can remain circular in an ideal two-body system. But no real system is completely isolated. The central star loses mass through radiation and stellar wind. Other planets tug from changing directions. Tides exchange energy. Relativity shifts the orbit. Passing stars add weak disturbances. Across deep time, the path evolves. Yet the orbit does not need to collapse. It can widen, tilt, precess, or remain nearly unchanged for ages. The circle, ellipse, and spiral are therefore not merely different shapes. They represent different physical stories. A circle suggests a special balance. An ellipse reveals conserved motion through changing distance. A spiral signals that energy or angular momentum is being transferred somewhere else, on the fabric. These stories blur because the material always drains motion. In the universe, their differences matter. A planet on an ellipse is not slowly failing to maintain a circle. It is following a stable natural path. A moon moving outward is not escaping gravity. It is receiving rotational energy through tides. A pair of black holes spiraling inward is not rubbing against space. It is radiating gravitational waves. The geometry guides every path. But the history of energy determines whether the path closes, widens, or contracts. Once that distinction becomes clear, the simple sheet gains a new value. Its imperfections become instructive. The visible spiral no longer stands as a complete image of orbit. It becomes a reminder to ask what carries energy away, what preserves angular momentum, and where the analogy stops. Gravity shapes the route, but the fate of the route depends on the larger system. A circle can endure, an ellipse can repeat, and a spiral can tighten only when something beyond pure two-body motion changes the balance. The planets of the solar system move around the Sun in the same general direction, and most of their orbits lie close to a shared plane. This order can look deliberate, as though the system begins with a finished design. Yet the pattern grows from a much less orderly beginning. The Sun and planets form from a vast cloud of gas and dust that contracts under its own gravity. The cloud is not perfectly still. It contains small currents, uneven motions, and slight rotations inherited from its environment. As gravity draws the material inward, these scattered motions do not cancel completely. One direction of rotation becomes slightly more important than the others. The difference may begin as a weak imbalance, but collapse magnifies it. Material moving inward must conserve angular momentum, so the shrinking cloud spins faster. The same principle appears whenever rotating matter contracts. A wide, slowly turning system can become a compact, rapidly turning one without receiving an external push. The original cloud therefore flattens and accelerates as it collapses, creating a broad, rotating disk around the young sun. Within that disk, most of the material travels in the same general direction, because the disk itself carries the dominant angular momentum of the cloud. The common motion of the planets is not added later. It is inherited from the structure in which they grow. At first, the disk is turbulent. Dust grains collide, gas streams cross, and clumps form only to be broken apart. Some particles move on tilted paths. Others travel against the dominant flow. Yet these motions do not survive equally well. A grain moving with a general rotation tends to meet nearby material at a relatively low speed. The collision may allow the grains to stick, merge, or settle into a more regular path. A grain moving in the opposite direction meets the surrounding flow at a much higher speed. Such collisions are more destructive. They shatter particles, remove energy, and reduce the chance that the opposing motion will persist. Over time, repeated interactions favour the direction already carried by most of the disk. The minority motions are not forbidden by gravity, but they are harder to preserve in a dense environment filled with collisions. The system gradually loses disorder, not because every unusual path is erased instantly, but because some paths are more stable than others. The stretched sheet demonstration can suggest this process when many small marbles move across the surface. If slightly more marbles begin in one direction, collisions and encounters can remove those travelling against the majority. Some strike the central mass, some scatter outward, some lose speed and settle into paths closer to the dominant motion. After enough interaction, a general direction emerges. The model is crude, and friction plays too large a role, but the pattern captures an important truth. Order can arise from selection among motions. The final system remembers a small preference that existed before the planets themselves formed. In the real solar nebula, gas drag is especially important. Small solid particles move through gas, and the gas exerts resistance on them. A particle whose orbit differs strongly from the surrounding gas loses relative motion. Its path becomes more circular and more closely aligned with the disk. Larger bodies respond less strongly to gas drag, but collisions and gravitational encounters continue the process. As planetesimals grow, they scatter one another, merge, or are removed. The population that remains tends to share the disk's overall rotation. The common direction is therefore both inherited and refined. The cloud supplies the net angular momentum, while the disk environment removes much of the motion that conflicts with it. This does not mean every object ends in perfect agreement. The solar system preserves exceptions. Some moons orbit their planets in unusual directions. Certain comets travel on steeply tilted or even retrograde paths. Small bodies can be captured, scattered, or disturbed long after the main disk has vanished. A giant impact can tilt a planet's rotation. Close encounters can reverse a moon's orbit or send an asteroid onto a strange trajectory. The large pattern remains clear, but the exceptions record later events. They show that the solar system is not mechanically uniform. Its present order rests upon an early common motion modified by billions of years of collisions, migrations, and gravitational disturbances. Even the planets do not orbit within exactly the same plane. Their paths are tilted by small amounts, and their orbital shapes differ. The word plane describes a broad arrangement rather than a perfectly thin sheet. The planets occupy a shallow three-dimensional region around the Sun. Still, compared with random orientations, the alignment is striking. This shared plane forms because the contracting cloud cannot keep large motions in every direction. Collisions between streams remove motion perpendicular to the dominant rotation more efficiently than they remove motion around the center. Gas and dust crossing above and below the emerging midplane collide, radiate energy, and settle. Rotation around the central axis survives because angular momentum must be conserved unless it is transferred elsewhere. The cloud therefore collapses most easily along the direction of its rotation axis and less easily across the rotating plane. The result is a disk. The same physics appears throughout the universe. Young stars are often surrounded by rotating protoplanetary disks. Material falls inward, but angular momentum prevents it from dropping directly onto the star. It spreads into a flattened structure where planets may form. Around black holes, gas also settles into accretion disks, though the temperatures and speeds become far more extreme. Spiral galaxies contain flattened stellar disks shaped partly by shared rotation, though their formation involves dark matter, mergers, and long gravitational evolution. Across very different scales, rotation and collapse repeatedly create planes. Gravity draws matter inward, while angular momentum resists direct collapse. The balance produces a disk rather than a simple sphere. The direction of rotation itself has no universal preference. Clockwise and counterclockwise depend on the chosen viewpoint. Seen from one side, the solar system turns one way. Seen from the opposite side, it turns the other. Physics does not favour either label. What matters is consistency within the system. The original cloud possesses a net spin, however small, and that spin defines the shared direction for the disk that follows. Another star-forming cloud elsewhere may rotate in any orientation, across a galaxy. Planetary systems can point in many different directions because their parent clouds inherit different motions. The order is local rather than cosmic. Each system develops around its own angular momentum. The young solar system also changes as its planets grow. Large bodies stir the disk gravitationally, sending smaller objects into new orbits. Some are thrown inward toward the Sun. Others are scattered outward into distant reservoirs. Growing planets can migrate through the disk as they exchange angular momentum with gas and planetesimals. Their movement reshapes the material around them and may alter the final spacing of the planetary system. Despite this activity, the dominant direction remains difficult to overturn because it belongs to the angular momentum of the whole disk. Reversing a planet would require a major transfer of energy and angular momentum. Smaller objects are more easily redirected, but large planets retain the original rotational memory. The common direction of motion therefore reveals something about the solar system's origin that remains visible long after the birth cloud disappears. The gas is dispersed, most loose dust has been gathered, expelled, or destroyed. The young sun has settled into a stable star, yet the planets continue to circle in the direction established during collapse. Their motion is a surviving fossil, not a fossil of rock but of momentum. Every orbit carries information about the cloud from which it forms. The plane, direction, spacing, and remaining exceptions together preserve fragments of a vanished environment. Gravity shapes the collapse. Collisions remove conflicting motions. Gas smooths the paths, and conservation laws protect the dominant spin. From a turbulent cloud emerges a system that appears calm and coordinated. The planets do not choose a common direction, and no separate force arranges them after formation. They inherit it from the rotating disk, where tiny initial imbalances grow into lasting architecture. The same principle that guides a marble around a curved surface also works within a larger history of matter. Curvature determines possible paths, but the distribution of motion decides which paths become populated. The solar system's shared rotation is therefore not only a feature of present gravity, it is a record of how gravity gathers matter, how collisions erase some motions while preserving others, and how a faint turn in an ancient cloud becomes the enduring rhythm of worlds. The solar system appears almost flat when viewed across its full width. The planets do not surround the sun like bees around a hive, each moving on a randomly tilted route. Instead, their orbits occupy a broad but relatively thin disk, with most of the major planets remaining close to a common plane. Each orbit carries its own small tilt, and the smaller bodies preserve a much wider range of angles. Yet the overall pattern is unmistakable. The planets share not only a common direction of motion but also a common geometric layer. That layer is the surviving shape of the disk in which they form. Gravity pulls the original cloud inward from every direction, but rotation prevents the collapse from remaining spherical. Material can fall more easily toward the middle from above and below than it can fall directly toward the center across the direction of rotation. Motion around the central axis is protected by angular momentum. While motion perpendicular to the emerging disk is gradually reduced, the cloud therefore flattens. A thick, turbulent volume becomes a thinner rotating structure, and within that structure the future planets begin to grow. The flattening is not produced by gravity alone. Gravity draws matter together, but collisions determine which motions survive. Particles moving above and below the disk repeatedly cross the crowded central region. When they collide with material traveling closer to the main plane, part of their vertical motion is converted into heat, vibration, deformation, or fragmentation. Gas also resists bodies that move through it at an angle. Each passage removes a little of the motion that carries the body away from the disk. Repeated over countless encounters, this damping process turns a three-dimensional swarm into a flatter population. In the young solar system, vertical movement above and below the disk is damped more efficiently than the shared rotation around the Sun. The result is not complete stillness, but a narrowing of the range of orbital inclinations. Inclination is the angle between an orbit and a chosen reference plane. A body with low inclination remains close to that plane. A body with high inclination rises far above it, and later passes far below it. In a dense protoplanetary disk, high inclination paths are difficult to maintain because they cut through gas and debris at large relative speeds. Each crossing creates opportunities for drag, collision, or gravitational deflection. Low inclination bodies move more nearly with the local flow and encounter their surroundings more gently. They are therefore more likely to survive, merge, and grow. This selection slowly favours a flatter architecture. The process also helps explain why planet formation is concentrated near the disk's midplane. Gas pressure, gravity, and drag cause dust grains to settle toward the densest central layer. Small grains remain stirred by turbulence, but larger particles respond more strongly to settling. As they gather near the midplane, the chance of collision increases. Some collisions lead to sticking, especially among small particles. Larger bodies grow through a mixture of impacts and gravitational capture. Once an object becomes massive enough, its gravity draws in material from a wider region. The first planetesimals continue to interact within the same flattened zone. Their growth reinforces the planar pattern, because most available material already occupies it. A planet assembled from a disk inherits the disk's angular momentum and general orientation. Yet the young system remains unsettled. Growing worlds disturb one another. Their gravity raises inclinations, stretches orbits, and scatters smaller bodies. Two planetesimals passing close together can exchange energy and leave on more tilted paths. A developing giant planet can send debris far above the original disk or cast it toward distant regions. Some bodies collide and merge, others are thrown into the Sun, ejected into interstellar space, or stranded in remote reservoirs. Gravitational stirring therefore works against perfect flatness. It thickens the disk by producing a range of inclinations. At the same time, gas drag, collisions, and dynamical friction tend to cool the system. Dynamical friction is not ordinary rubbing. It is the collective gravitational effect through which a massive body moving among many smaller bodies transfers some of its irregular motion to them. The large body's orbit can become more circular and less tilted while the smaller population gains energy. The young system develops through a balance between stirring and damping. The final plane is neither perfectly smooth nor randomly disordered. It is the residue of both processes. The stretched fabric model can hint at this evolution when many marbles move near a central depression. Marbles launched at steep angles cross the crowded middle and suffer frequent collisions. Some lose energy, some change direction, and some leave the surface entirely. Those moving near the dominant plane encounter fewer disruptive crossings and can remain in recognizable orbits for longer. Yet the analogy breaks down because the fabric has only one visible surface. Real planetary motion occupies 3 dimensions, and the early disk has thickness. Bodies pass above and below one another, while gas fills the surrounding region. The sheet can show a preferred plane only by placing everything on that plane from the beginning. It cannot fully demonstrate how the plane emerges from a cloud with depth. The real flattening requires the gradual removal of vertical motion within a rotating volume. The surviving disk is also not infinitely thin because several processes keep it stirred. Turbulence in the gas lifts small particles. Young planets gravitationally excite nearby debris. Collisions create fragments with new directions. Passing bodies and resonances alter inclinations over time. A resonance occurs when orbital periods form a repeating relationship, allowing small gravitational tugs to accumulate. Some resonances stabilize paths, while others increase their tilt. The planets themselves exchange weak gravitational influences that cause their orbital planes to precess. Precession is a slow change in the orientation of an orbit. As a result, the solar system has no single plane that every object follows exactly. Astronomers choose reference planes, such as the plane of Earth's orbit or the invariable plane defined by the system's total angular momentum. The differences reveal that the architecture is close to flat but never perfectly rigid. The major planets preserve the disk most clearly because they contain most of the surviving planetary mass and form within its dense central region. Smaller populations record a more complicated history. The asteroid belt includes bodies with a range of inclinations produced by resonances, collisions, and planetary perturbations. The distant Kuiper belt contains a relatively cold population with low inclinations and a hotter population on more tilted paths. The terms cold and hot refer mainly to orbital motion rather than temperature. The colder group preserves more of the early disk's calm geometry, while the hotter group carries evidence of later scattering and migration. Comets arriving from the distant Oort cloud can approach from almost any direction. Their nearly spherical distribution suggests that they were scattered far from the original plane, and later disturbed by passing stars and the gravity of the galaxy. These exceptions do not erase the disk-shaped origin. They reveal how later evolution can lift objects out of it. Large planets also preserve signs of disruptive events. A major collision can tilt a planet's spin axis even while its orbit remains near the common plane. A moon can be captured onto a retrograde or strongly inclined orbit. Planetary migration can rearrange resonances and scatter whole populations. The plane therefore records origin, while deviations record history. The flatter the major architecture remains, the more clearly the original disk survives beneath later disturbances. The more tilted an individual object becomes, the more likely its path has been altered by collision, capture, scattering, or long gravitational interaction. The solar system can be read as two overlapping records, a broad planar pattern inherited from formation, and a collection of exceptions written by subsequent events. This pattern extends beyond the solar system. Many planetary systems around other stars also show evidence of shared orbital planes, especially when several planets repeatedly cross the face of the same star as seen from Earth. Multiple transits imply that the planets often occupy a relatively flat arrangement. Other systems appear more tilted or disturbed, perhaps because of close encounters, distant companions, or past instability. The range suggests that disk formation commonly begins with flatness, while later evolution decides how much survives. The plane of the planets is therefore not a decorative feature of the solar system. It is a physical memory of collapse, rotation, collision, and selection. Gravity gathers the material, angular momentum gives it a shared turning motion, and repeated interactions remove much of what moves too far above, below, or against the dominant flow. What remains is a broad, enduring layer of worlds. It is not perfectly level, and it is not untouched by chaos, but it preserves the direction and shape of a vanished disk whose gas and dust disappeared long ago. The quiet alignment of the planets is the fossil outline of that ancient structure, still traced by their motion around the sun. The stretched sheet model becomes most valuable at the moment it begins to fail. Its first impression is powerful. A heavy sphere creates a depression, Smaller spheres curve toward it, and greater mass produces a stronger distortion. Yet every visible feature carries hidden assumptions that do not belong to real space-time. The sheet has an edge, a top, a bottom, material tension, and a downward direction. It sits inside a larger room and depends on Earth's gravity to make marbles roll into the central hollow. None of these features describes the geometry of the universe. They are supports for the analogy, useful because human vision understands surfaces and slopes and motion. The danger appears when the support is mistaken for the structure it represents. Real space-time is not a fabric laid across an external frame. It does not sag into a surrounding dimension under the weight of stars. It has no cosmic underside toward which objects descend. Curvature is an internal property, revealed by how distances, paths, and clock rates relate to one another within the geometry itself. Travellers on Earth can detect the planet's curvature by measuring large triangles, following long routes, or observing how initially parallel paths converge. In the same way, observers within space-time detect curvature through the behaviour of light, freely falling bodies, and precise clocks. The shape is known from what happens inside it. The sheet also reduces a four-dimensional theory to a two-dimensional picture. It represents space as a surface and leaves time almost entirely absent. General relativity, however, describes space-time as one connected structure. Near a massive body, spatial relationships change, but so does the passage of time. Clocks closer to Earth run more slowly than clocks farther away. Near a black hole, the difference becomes extreme. A model that shows only a spatial funnel therefore hides one of gravity's most important features. In weak fields, the curvature of time contributes strongly to the acceleration that appears as falling. The marble rolls inward because the cloth slopes downward in ordinary gravity. But a real falling object moves because its natural path through curved space-time leads that way. The similarity of the motion can conceal the difference in cause. Another problem lies in the sheet's use of gravity to explain gravity. The large sphere presses into the fabric because Earth pulls it downward. The smaller sphere follows the slope because Earth also pulls it downward. Without gravity beneath the model, the demonstration would not work in the same way. It therefore explains one gravitational effect by borrowing another, creating a circle that is acceptable for visualization but incomplete as an explanation. Real general relativity requires no external field beneath space-time. The geometry itself defines the paths. The sheet also makes curvature appear as a pit extending below the central object. In reality, a spherical body curves the surrounding space-time in every direction. Earth's influence is not a funnel beneath the planet. It surrounds Earth, and satellites can orbit in planes tilted at any angle. The fabric places all motion on one surface, forcing every orbit into the same plane. This is convenient for display, but it hides the three-dimensional freedom of real space. Several bodies can occupy crossing orbital planes without touching. On the sheet, their paths must intersect because they share one surface. The model therefore exaggerates collisions and cannot represent the full geometry of interacting systems. It also gives the central mass a literal size within the surface, and often leaves it supported by the fabric. A real body does not sit on space-time like a weight on cloth. It is part of the space-time system. Its matter and energy contribute to curvature throughout the region it occupies and beyond. There is no separate stage that exists untouched beneath it. In general relativity, matter influences geometry, and geometry influences the motion of matter. The relationship is not between an object and a passive material background. It is a coupled structure in which the supposed stage responds dynamically. The fabric can ripple when disturbed, which seems to resemble gravitational waves, but even this resemblance needs caution. Ripples on cloth travel through a material whose fibers move within surrounding space. Gravitational waves are changes in the geometry of space-time itself. They stretch and compress distances in alternating directions as they pass. No substance vibrates inside a larger arena. The arena is what changes. The sheet can suggest propagation, but it cannot reproduce the nature or pattern of the waves accurately. Friction creates another major distortion. Every marble loses energy as it rolls, its orbit shrinks, and it spirals inward. This makes stable orbits look temporary by nature. Real planets do not lose energy merely because they travel through curved space-time. In an ideal, isolated system, an orbit can continue without decay. Energy loss requires a mechanism such as atmospheric drag, tidal interaction, radiation, or gravitational waves. The cloth supplies several mechanisms automatically through deformation, sound, heat, and air resistance. As a result, the demonstration turns nearly every orbit into a spiral and makes collision appear inevitable. The model can show how sideways motion becomes a loop, but it cannot show the long-term stability of that loop. The surface also creates a preferred state of rest. The frame stands still in a room, and the central sphere is often placed at the center, as if it defines absolute stillness. Relativity contains no universal stationary frame. Motion is described relative to chosen observers, and even the central body responds to companions. A star moves around a barycenter. A galaxy travels within a group. A black hole can recoil after a merger. The sheet encourages a picture in which one mass creates the landscape, and everything else responds while the creator remains fixed. A more accurate treatment allows every body to participate, but the fabric's friction and support prevent the mutual motion from matching reality. The analogy also suggests that deeper curvature always means a stronger downward slope. Real curvature is more complicated. It cannot be summarized by a single depth. Different aspects of space-time curvature describe how paths converge, how clocks differ, and how tidal effects stretch or compress objects. Rotation adds further complexity. A spinning mass does not merely deepen a symmetric depression. It drags the surrounding space-time in the direction of its rotation, an effect called frame dragging. Near a rotating black hole, this twisting becomes profound. The sheet has no natural way to display such a change without being mechanically spun. And even then, the motion would come from friction with material rather than geometry associated with angular momentum. The model usually treats mass alone as the source of curvature, reinforcing the simplified statement that matter bends space. General relativity is broader. Energy, momentum, pressure, and stress all contribute. A beam of radiation carries energy and therefore affects space-time, though the effect is extraordinarily small in ordinary situations. The geometry responds not just to how much matter exists, but to how energy and momentum are distributed and moving. No collection of weighted balls on fabric can display this full relationship. Even the phrase that mass bends space-time can mislead if taken too literally. Curvature is not something that happens after matter is placed into an already complete arena. Geometry and contents are solved together. The equations connect them, but they do not reveal a mechanical substance beneath the connection. The theory describes how curvature relates to energy, and how free objects move through that curvature. It does not say that space-time is woven from threads or stretched like rubber. The word fabric is metaphorical. Its usefulness lies in suggesting continuity and deformation, not material composition. Once this is understood, the model can be used with greater precision. The central depression illustrates that mass changes nearby paths. The rolling marble illustrates that motion can curve without an ordinary sideways push. Two weights illustrate overlapping influence. A changing surface hints that geometry is dynamic. Each lesson remains valuable when paired with its limitation. The depression is not literal depth. The marble is not a planet rubbing against space. The sheet is not all of space, and the room around it is not a higher cosmic dimension. Time remains mostly invisible, stable orbits are poorly represented, and the central body is too easily treated as fixed. The analogy therefore serves as a doorway rather than a destination. It helps ordinary intuition release the idea of gravity as a distant pull, then must be set aside before it builds a new misconception. Beyond the fabric lies a geometry that cannot be fully pictured because it includes time, has no external downward direction, and changes according to all forms of energy. Its reality is not established by resemblance to cloth, but by precise predictions, the bending of light, the shifting of Mercury's orbit, the unequal rates of clocks, the behavior of binary stars, and the arrival of gravitational waves. The sheet makes curvature visible, but the universe reveals curvature through measurement. The model ends where the deeper theory begins. The Earth and Moon are often pictured as a simple pair, a large world at the centre and a smaller companion circling around it. That picture is useful, but it hides the shared motion beneath the familiar orbit. Earth does not remain perfectly still while the Moon travels around it. Both bodies respond to the same gravitational relationship, and both move around a common centre of mass. This point lies inside Earth because Earth is much more massive, yet it is displaced from Earth's centre. As the Moon completes its orbit, Earth follows a smaller loop around that internal balance point. The result is a slow, continuous wobble carried through the larger yearly motion around the Sun. The wobble is not an imperfection added to the Earth-Moon system, it is the system. Every orbit contains this mutual response, even when one body is so dominant that the smaller countermotion is easy to ignore. In the language of curved space-time, Earth and the Moon each alter the geometry around them. The Moon moves mainly through the curvature associated with Earth, but Earth also moves through the weaker curvature associated with the Moon. Their paths are joined. Neither body occupies a fixed background while the other reacts. The geometry changes with both, and the pair follows that changing structure together. A stretched fabric can hint at this when two weighted spheres are placed on the surface. The larger sphere makes the deeper depression, while the smaller sphere creates a shallower one nearby. If both are free to move, the large sphere shifts slightly as the small sphere travels around it. The motion may be difficult to see because friction holds the larger mass and drains energy from the smaller one. But the underlying lesson remains. The central object is not truly central in the sense of being motionless. The balance point belongs to the pair. In the real Earth-Moon system, the shared centre moves with them around the Sun, tracing a gently rippled path rather than a perfectly smooth one. Earth and the Moon therefore travel through the solar system as a gravitational partnership. The Sun acts strongly on both, and the difference between its pull on the near and far sides of the pair contributes to the complexity of their motion. The Moon is not simply circling an isolated Earth, it follows a path shaped by Earth and the Sun together. From one viewpoint, the Moon loops around Earth. From another, both bodies follow neighbouring curves around the Sun, with the Moon weaving slightly inward and outward relative to Earth. Neither description is false. Each chooses a different frame and emphasizes a different scale. General relativity allows the same motion to be described through geodesics in the combined space-time geometry, though for most Earth-Moon calculations the older gravitational approximation remains accurate enough. The Moon's influence on Earth appears most clearly through tides. The side of Earth facing the Moon is slightly closer to it than the far side, so the gravitational effect is not exactly the same across the planet. This difference stretches Earth and its oceans along the Earth-Moon line. A tidal bulge forms on the near side, while another appears on the far side because Earth itself is pulled more strongly than the more distant water there. The oceans do not simply rise under the moon as a single mound. The whole planet participates in a changing gravitational field, and the difference across its diameter produces the tidal pattern. Earth's rotation carries the oceanic bulges through coastlines and basins, where the actual tides become far more complicated. Continents block the flow, sea floors shape it, and local geography can amplify or suppress the rise and fall. Yet beneath that complexity lies the shared geometry of two bodies acting across an extended world. Tides also reveal that the Earth-Moon relationship evolves. Earth rotates more quickly than the Moon orbits, so the tidal bulge is carried slightly ahead of the line connecting the two bodies. The Moon pulls backward on this displaced bulge, gradually slowing Earth's rotation. The bulge pulls forward on the Moon, giving it orbital energy and causing its orbit to widen very slowly. Earth's days become longer across deep time, while the Moon recedes. The change is tiny from year to year, but significant across geological ages. The present system is therefore not fixed. It carries a record of energy passing between spin and orbit. The shared center remains, but the scale and timing of the dance slowly change. This transfer also shows why the stretched sheet spiral must be interpreted carefully. On the fabric, the smaller sphere usually loses energy and falls inward because friction removes motion. In the Earth-Moon system, tidal interaction causes the Moon to move outward. Gravity alone does not dictate that every orbit shrink. The direction of change depends on where energy and angular momentum move. A different Moon around a slowly rotating planet may spiral inward. The geometry guides the motion, but the exchange decides whether the separation grows or contracts. The shared curvature also shapes spacecraft trajectories. A craft leaving Earth for the Moon does not travel across a simple empty gap and then suddenly enter lunar gravity. It moves through a continuous gravitational landscape produced by Earth, the Moon, the Sun, and smaller influences near Earth. Earth dominates the motion. Farther away, the Moon's role becomes more important. There is no sharp wall where one field ends and the other begins. The craft's path bends gradually through the combined geometry. Mission planners use this landscape rather than fighting it. By choosing the right launch time, speed, and direction, a spacecraft can follow a route that reaches the Moon with relatively little correction. The journey becomes an exercise in entering the correct natural path. Some trajectories loop around the Moon and return toward Earth even if propulsion fails after departure. Such free return paths are possible because the craft is placed on a route that threads through the moving Earth-Moon geometry and naturally bends back toward the home planet. Drawn in a rotating frame that keeps Earth and the Moon in roughly fixed positions, the path may resemble a broad figure 8. In ordinary space, the actual motion is more complex because the entire system travels around the Sun. The figure is therefore not a literal track carved into space. It is a useful representation of motion relative to the two main bodies. The possibility of such a route reveals how geometry becomes navigation. A spacecraft does not need to be pushed along every part of the journey. Once given the proper initial motion, it falls through the shared gravitational structure. Tidal forces gradually remove the difference between its spin rate and orbital rate until this locked state emerges. The far side is not permanently dark, but it is permanently turned away from Earth, except for a slight rocking motion that reveals narrow regions beyond the average edge. This synchronization is another form of shared evolution. Earth changes the Moon's rotation. The Moon changes Earth's rotation, and both alter their orbit through the exchange. Even their shapes are slightly influenced by the mutual gravitational field. The two bodies remain distinct worlds, yet their motions cannot be fully understood in isolation. The stretched fabric reduces this partnership to two depressions on a surface. But the real system includes changing time, three-dimensional motion, tides, rotation, and the influence of the sun. The model nevertheless points toward the essential idea: every mass responds. Every orbit has a counter-orbit. Every apparently fixed center hides a smaller motion. Earth carries the moon around the sun, but the moon also carries Earth around their shared balance point. Their mutual curvature produces a quiet wobble, a slow exchange of energy, and a network of paths through which spacecraft can move. The familiar moon in the night sky is therefore not merely an object circling a stable world. It is one half of a coupled gravitational system whose geometry is continually written by both bodies and whose motion reveals that no participant in gravity remains entirely still. Between Earth and the moon, space is not empty in any simple sense. It contains no road, no visible rails, and almost no air. Yet motion there is guided by a landscape as real as any mountain valley. The landscape is gravitational. Earth shapes it strongly. The moon shapes it more gently. And the sun adds a wider influence that never disappears. A spacecraft crossing this region does not travel in a straight line through a passive void. It enters a changing geometry created by moving bodies, and its route bends according to where it begins, how fast it moves, and when it departs. Navigation between worlds therefore depends less on forcing a craft along a rigid path and more on placing it onto a natural trajectory that gravity is already prepared to support. This is why lunar flight paths often look like loops rather than simple arcs. The moon is moving around Earth, Earth is moving around the sun, and the launch site itself is rotating with the planet. Every successful route must anticipate where the moon will be when the craft arrives. At launch, the vehicle climbs through Earth's atmosphere and accelerates until it reaches a temporary orbit. At the correct moment, an engine burn increases its speed and sends it onto a path that rises away from Earth. The burn does not push the spacecraft all the way to the moon. It changes the craft's initial conditions. After that, gravity takes over. The spacecraft continues to fall through curved space-time, but its sideways motion and growing distance from Earth shape the fall into a long outward arc. The moon's influence becomes more important as the craft approaches. The route is therefore a transfer between overlapping gravitational regions rather than a movement from one isolated field into another. There is no clean border where Earth's gravity stops and lunar gravity begins. Both are always present. The stretch sheet model can suggest this by placing two heavy spheres on the same fabric. A small marble rolled through the surface responds to the combined shape. Near the larger sphere, the path is dominated by the deeper depression. Near the smaller sphere, the shallower hollow changes the trajectory more strongly. Between them, the marble follows a route shaped by both. Yet the demonstration remains imperfect because the two spheres often sit still while the real Earth and Moon move continuously. The gravitational landscape rotates and shifts with them. To describe this motion clearly, mission planners often use a rotating frame in which Earth and the Moon appear nearly fixed. In that frame, some paths form broad loops and crossing shapes that would look different in a frame centered on the Sun. A figure 8 can appear when the route is drawn relative to Earth and the Moon, even though the spacecraft traces a smooth path while the entire system moves around the Sun. One of the most important examples is the free return trajectory. This route is designed so that a spacecraft sent toward the Moon can pass around it and return toward Earth without requiring a major engine burn at the Moon. The craft is placed on a path that uses the combined gravity and motion of the Earth-Moon system. If the planned lunar orbit insertion does not occur, the spacecraft can continue around the Moon and fall back toward Earth. Small corrections may still be needed, and the exact design depends on mission goals, launch timing, and the chosen lunar encounter. Yet the underlying principle is powerful. Geometry itself provides a route home. The spacecraft carries enough motion to reach the Moon, but not so much that it escapes the Earth-Moon system entirely. The Moon bends the path, changing the craft's direction so that Earth becomes the natural destination once more, in a rotating diagram. The motion may resemble a loop around Earth joined to another loop around the Moon. The crossing at the centre gives the familiar figure-8 appearance. This visual form helps explain the route, but it should not be mistaken for a physical track suspended in space. The spacecraft never passes through a marked intersection. The figure exists because the coordinates move with the two bodies. In another frame, the trajectory becomes a different curve. The geometry of space-time and the motion of the bodies determine the sequence. The free return path reveals a broader truth about orbital navigation. Fuel is often used most efficiently in short, carefully timed changes rather than in constant thrust. An engine burn changes velocity. Gravity then reshapes the resulting path over hours or days. A small correction made early can produce a large change later, because the craft is placed on a slightly different geodesic. A burn that's correct in speed but late by a small amount can shift the arrival point by a great distance. Mission design therefore depends on precise clocks, accurate tracking, and repeated calculations. Guidance systems compare the actual motion with the planned trajectory. When the difference becomes significant, a correction burn selects a new path through the same landscape. The Moon can also be used to alter a spacecraft's energy relative to Earth. During a close pass, the craft exchanges a tiny amount of momentum with the moving Moon. The Moon changes imperceptibly, while the spacecraft's speed and direction can change noticeably. This is a gravitational assist. The effect depends on the direction of approach. Passing behind the Moon in its orbit can increase the craft's energy relative to Earth, while passing ahead can reduce it. The Moon becomes a moving source of curvature whose motion can be borrowed. No physical contact occurs, and no fuel is consumed during the encounter itself. The same principle is used on a larger scale when spacecraft pass planets to reach the outer solar system or move closer to the Sun, between Earth and the Moon. These techniques reveal that trajectories are not merely responses to static masses. They are interactions with moving gravitational systems. Certain routes take advantage of regions where the combined effects of Earth and the Moon create special patterns of motion. In a rotating frame, there are locations where a small object can remain in a repeating relationship with the two larger bodies. These are often described as balance points, though gravity does not vanish there. Instead, the object's orbital motion and the pulls from Earth and the Moon combine in a particular way. Some of these regions are unstable, so a small drift grows unless corrected. Others allow families of looping orbits nearby. Spacecraft can move around these regions on paths that seem to hover relative to Earth and the Moon while actually following continuous orbits. Such routes can reduce fuel use, support communication, or provide useful observing positions. They extend the idea of geometry as navigation beyond the direct journey from one surface to another. The path itself becomes a resource. Every kilogram of propellant carried into space requires more energy at launch. Mission planners therefore search for trajectories that let gravity perform as much of the work as possible. A fast route may demand more fuel. A slower route can sometimes use weaker transfers, extended loops, or carefully timed encounters to reach the same destination with less propulsion. A crewed flight may value speed and safety, while a robotic probe may accept a longer journey to conserve fuel. The gravitational landscape offers many possible paths, each with different costs, risks, and timing. Navigation is the art of selecting among them. The stretched fabric captures only the simplest form of this art. A marble can be rolled toward two depressions and made to loop around one before returning toward the other. With practice, a rough figure 8 may appear. The demonstration shows that a moving object can be redirected without being touched. Yet friction quickly drains the marble's energy. The masses remain too fixed, and the fabric cannot show the changing rate of time. Real lunar trajectories unfold in three-dimensional spacetime, influenced by the sun, the shape of Earth, the uneven moon, and the motion of every body involved. Their precision is far beyond what the sheet can reproduce. Still, the visible loop contains the essential insight. A route through gravity is not imposed upon empty space. It emerges from the structure already present. The spacecraft follows a carefully chosen fall, moving from one curved region into another while engines intervene only at selected moments. Between two worlds, geometry becomes a silent form of guidance. Earth releases the craft onto an outward path. The moon bends that path, and the combined system can return it home. The apparent emptiness between the worlds is therefore full of possibilities, each one written into the curvature and motion of space-time. The stretched sheet begins with a quiet promise. It offers a surface that can bend, a mass that creates a visible hollow, and smaller objects whose paths curve in response. For ordinary gravity, this picture is often enough to open the door. It suggests that space and time are not passive, that matter changes the geometry around it, and that motion can follow curvature without an invisible hand pulling from a distance. Yet the universe carries this idea far beyond anything a sheet can display. Space-time does not merely hold static depressions around stars and planets. It can ripple, expand, twist, and evolve across the larger scales. The model remains useful only by admitting that these deeper behaviors lie outside its reach. Gravitational waves provide the clearest example. When massive bodies accelerate, they create changing distortions in space-time. If the motion is sufficiently violent and uneven, those distortions travel outward as waves. Two black holes orbiting one another form a rapidly changing gravitational pattern. As they draw closer, the pattern sweeps faster, sending ripples away through the universe. The waves do not move through space as sound moves through air or as water waves move across an ocean. They are changes in the geometry of space-time itself. As a gravitational wave passes, distances stretch in one direction and compress in another, then reverse. A cloth surface can be shaken to produce ripples, but the resemblance is limited. The cloth vibrates inside surrounding space, while gravitational waves are vibrations of the geometry that defines distance. No external room is required. The wave carries energy, moves at the speed of light, and preserves information about the source that created it. A merging pair of black holes may be completely dark, yet the changing curvature announces the event across immense distances. The signal reveals the masses and motion of objects that cannot be seen directly. In this way, the universe is observed not only through light, but also through the movement of space-time itself. The sheet cannot reproduce this fully because its ripples depend on tension, gravity, and material fibers. It can hint that geometry may be dynamic, but not that geometry can carry a signal without vibrating inside a larger background. Space-time also responds to rotation in ways the ordinary fabric picture cannot show. A spinning planet or star does more than create a symmetric gravitational field. Its rotation drags the surrounding space-time slightly with it. This effect is weak around Earth, but measurable. Near a rapidly spinning black hole, it becomes intense. The geometry is twisted so strongly that no object can remain stationary relative to distant space within a certain region. Motion around the black hole becomes partly compelled by rotating space-time itself. A spinning sheet might make marbles move with it. But that would happen because of friction between material surfaces. Frame dragging is different. It belongs to the geometry produced by rotating mass and energy. The distinction reveals the limit of mechanical analogies. They copy a visible outcome while relying on a cause absent from the real phenomenon. The greatest failure of the sheet appears at the scale of the universe as a whole. A sheet suggests a surface contained within a larger room, with edges that can be held or stretched. The universe has no known external frame around which its geometry is arranged. Cosmic expansion does not mean galaxies are flying outward from a central explosion into pre-existing emptiness. On large scales, the distances between widely separated regions increase because the geometry itself evolves. Galaxies that are not gravitationally bound become farther apart as space expands between them. No central point lies at the middle of this expansion. Every observer in a sufficiently uniform universe sees distant galaxies receding, much as every point on the surface of an inflating sphere sees other points move away. The sphere analogy is useful, but even it adds an external dimension that the universe doesn't require. The expansion belongs to the internal relationships between locations. A stretched sheet can imitate increasing distances if its edges are pulled apart, but the action needs hands, a frame, and an outside direction. Cosmic expansion requires none of these. It emerges from the behavior of spacetime under the contents and conditions of the universe. Matter tends to slow the expansion through gravity because matter attracts and clumps. Observations, however, show that the expansion of the universe is accelerating. Distant galaxies are becoming separated at an increasing rate on the larger scales. The name dark energy is given to whatever drives this acceleration. The term does not identify a known substance with familiar properties. It marks an unresolved part of the cosmic description. The simplest explanation treats empty space as having a constant energy density, often associated with the cosmological constant in Einstein's equations. As the universe expands, more space appears, yet this energy density remains constant in that model. The result is an influence that becomes increasingly important as matter spreads out. Other possibilities exist, but none has been confirmed as the final explanation. The evidence supports accelerated expansion, while the underlying cause remains uncertain. A classroom demonstration may try to represent dark energy by pulling a sheet outward or by using a surface that pushes objects apart. Such images can illustrate separation, but they risk turning dark energy into a conventional repulsive force acting from a location. The real effect is tied more closely to the changing geometry of the universe. It does not simply make nearby objects fly apart. Earth does not expand. The solar system does not expand in any noticeable way. And galaxies held together by gravity do not stretch with cosmic expansion. The effect becomes important across distances where local binding is weak and the overall geometry dominates. This selectivity is difficult to show with fabric, which stretches everything attached to it. Dark energy therefore exposes a second limitation. The sheet is local, while cosmic expansion is global. It shows how one mass changes nearby motion, but not how the entire geometry can evolve according to the average contents of the cosmos. It also cannot show that gravity can both gather matter and participate in accelerating expansion, depending on scale and distribution. On small and medium scales, gravity builds structure. Gas falls into dark matter halos. Stars form in galaxies. Galaxies gather into groups and clusters, and compact objects merge. On the largest scales, unbound regions move farther apart as expansion accelerates. These tendencies coexist. The universe grows more structured locally while becoming more separated globally. A single depression on elastic cloth offers no natural way to represent this layered behaviour. The model also leaves unanswered what spacetime actually is. General relativity describes its geometry with extraordinary success. Yet the theory does not explain whether spacetime is fundamental or emerges from something deeper. Quantum theory describes matter and the other known interactions in terms of fields and probabilities. But gravity resists a complete union with that framework. At very small scales or inside the most extreme regions, the smooth geometry of general relativity may no longer be enough. Black hole interiors and the earliest moments of cosmic history point toward conditions where quantum gravity becomes necessary. No confirmed theory yet provides a complete description. Spacetime may have a microscopic structure, or it may emerge from relationships more basic than distance and time. These possibilities remain speculative, but they arise from a real boundary in present knowledge. The sheet cannot approach this boundary because it begins by assuming a continuous material surface. It offers no clue whether geometry itself can be divided, fluctuated, or built from deeper elements. Its fabric is visible and tangible, while the true fabric is only a metaphor. What remains after the analogy is removed is a set of measured effects and a remarkably precise theory connecting them. Light bends near mass. Clocks run at different rates in different gravitational environments. Orbits shift. Rotating bodies drag space-time. Accelerating masses produce gravitational waves. The universe expands, and that expansion accelerates. These facts belong to one geometric framework, yet they resist a single ordinary picture. The curved sheet captures the first step, then falls silent. Beyond it, gravity becomes not merely the shape around objects, but the evolving architecture of the cosmos. It carries waves from collisions in darkness, guides light across curved paths, twists around spinning bodies, and stretches distances between galaxies. The deeper mystery is not that the analogy fails. It is that a theory built from geometry describes so much of reality while leaving its own foundation unresolved. Space-time behaves like a dynamic participant in the universe, but whether it is the final layer of nature or the visible surface of something deeper remains unknown. The sheet offers a beginning because it makes curvature familiar. The universe continues beyond the model, where geometry can move, expand, and perhaps emerge from a structure that no fabric can represent.